let's review solving two linear equations in two variables. This came up briefly in the last semester for us in our geometry, but it's such a fundamental thing. So algebraically, an example would be simply that we want to find x and y such that they not only satisfy one or the other of both these equations, they satisfy both of them at the same time, right? So x and y simultaneously, it's a word we often use to emphasize it's a simultaneous system of equations. And so they're supposed to satisfy both. Now, to get an idea of this, almost everybody graphs these things. So let's graph these. Let's really quickly see how you would do that by hand, right? We're pretty familiar with the y equals mx plus b form. So if we take that first equation and we move over the x and divide by 2, we get 3 minus 3 halves x. So it's got y-intercept 3. It's got slope minus 3 halves, so it's moderately sloping down. The other thing, remember, you can do is you can cover up the y, set it equal to 0, and solve for x. So the x-intercept is going to be 2. So it goes through 2, 0, as well as 0, 3. And it's this downsloping line right here. Not too bad, okay? And then the other one, minus x plus 3y equals 3. Again, we know what to do with that. Now here 3y is 3, or x plus 3, divide by 3. You get a 1/3 x, so that's your positive slope, plus 1. So it's sloping gently upward. It's going through 0, 1. And again, let's get the other intercept. If I cover up the y, set it equal to 0, x is minus 3. Okay. So I didn't include that in the picture because that's a little bit far off to the left. But you can see it's going through intercept 1 and going gently up. Okay. So now that I've graphed them, I can at least get an approximate solution just visually. And that's really appealing. And it's very nice. And I recommend doing that. It looks like we've got an approximate solution of about, oh, hello, that's the wrong shortcut there. That was fun. That's what I meant. Approximately 1 point, maybe 1-ish. It's not quite exactly 1. It's definitely to the right. And maybe like 1 1/4. But it definitely doesn't look like 1, 1 or anything incredibly simple. And the question is how to get the exact solution. Okay, so there's two common methods for this. And let's not have that distract us here. I really want to emphasize the elimination method. The OpenStax book calls this the addition method, but it's much more commonly called the elimination method. And it's to cleverly play off these equations against each other, and then to eliminate one of the variables and then make progress. Okay, so what I'm going to do is I'm going to rewrite those, but I'm going to multiply the second equation by 3, taking advantage of the most fundamental thing we know how to do with equations, which is you can always do the same thing to both sides of an equation. Certainly, you can multiply everything by the same constant. And then the more sophisticated thing to do is that I'm going to add the left-hand sides and add the right-hand sides. The reason that's legal is it's really the same thing I just said. If let's say I think of this as the equation that I'm manipulating, I can definitely add 9 to both sides of the equation, right? So let's take this guy. I can definitely add 9 to both sides of that, right? But here's the thing. This is 9 written in a much more complicated looking way. But this equation says I'm only interested in x-y pairs such that this combination of x and y is equal to 9. So I can totally add this to, oops, that's the wrong thing. Okay, I can totally add these guys to these guys. Now, if you have it set up in columns with the x's and the y's and the constants kind of lined up, you don't even have to write it out in this way, and I wouldn't usually. I would just say just put a bar under all this, like a usual addition problem, and just add, right? 3x plus minus 3x, that's a 0x. That's the whole point of doing this. And then plus 11y equals 15. So the reason it was smart to multiply the bottom equation by a 3 is it made these into equal and opposite coefficients, so that when I added them, it canceled. So you can either make the coefficients equal and opposite and add the equations, or you can make them equal and subtract the equations. But we'll do a bunch of examples in class. Okay, so I'm almost done for y at least. Don't forget, though, that's only half the story. This is absolutely the turning point. We've got one of the variables. It's going to be easy to find the other, but don't just stop here. So y is 15/11. Notice that's just a little bit bigger than 1.5. Let's do a reality check. Oh, yeah. A little smaller than 1.5, rather, because 15/10 will be 1.5. So it looks pretty good, okay? And then we can just plug into either one of the equations down here and solve for x. Just maybe the first one, just for fun. So I'm going to plug in that known value for y. I'm going to have to deal with the fractions. So 6 minus 30 over 11, which is 66 minus 30 over 11, which is 36. Whoa, nope. 36 over 11. It's not happening for me today. It will get there. We'll get there, I swear. Okay, and then divide by 3, I get 12/11. Aha. Okay, so that's just a little bit bigger than 1. This is a little bit less than 1.5, and that does make sense with what we saw here visually, and I was getting something like this. So I was a little bit low on this one. It's not quite that low, but it's definitely a little under 1.5. Okay, so that's an example of the elimination method. I could have chosen to eliminate y and solve for x instead, but like I said, we'll get practice in class with that. What about the substitution method? So let's bring that up. Like I said, elimination is much more powerful for more complicated linear equations that we do later. But substitution is more powerful when you have like x squared or x cubed or complicated functions that aren't just linear functions. So what would that look like here? We would just pick one of the variables in one of the equations, and then substitute in the other. So let's see how that works. Let's say I'm going to solve for y in terms of x here. Sometimes you can sort of see that one way is going to be easier than the other, but usually it really doesn't matter. So, of course, this is actually exactly what I did to get the point slope or the slope intercept form. So I actually had already done that for different reasons to get the graph. Okay, so that now the key is I'm going to substitute that in the other equation. So this is another very powerful thing about algebra, and that's that if I know that y is the same as 3 minus 3 halves x, whenever I see a y in any other context, including in this other equation, I can go ahead and substitute that in. Hey, that's an equation only involving x. I'm going to have to be careful to break that out. So let's see, 9 halves x equals 3. Okay, I'm going to need to collect the terms in front of the x. So let's say that's minus 2 over 2. So minus 2 over 2 minus 9 over 2. So that's minus 11 halves x. Notice the 11 coming in. That's not super surprising. And then I can also subtract the 9. Okay. And now I'm going to multiply by minus 2/11. And the minus signs cancel, and I get 12/11 like I had before. Okay, so that's good. The last step is almost exactly the same. You just use the value of the variable you just got to find the other one. Now, it happens to be that I solve for x in this one first, and I'm going to get y in terms of that. Now, that's particularly easy here because, I already have y solved for x. So that's kind of a nice thing about the substitution method. You're just going to plug that in and simplify. So 3 minus, we get a little cancellation, 12 over 2 is 6, so 18/11, or 33 minus 18 over 11, and that's 15/11. And that's what we got before. Okay, so that's the two common methods. In the next video, I'm going to talk briefly about what can go wrong and what's some important special cases.